define a distinct time range within which your collisions will be active. But they're a curse because, you know, if you use them and you don't forget, and you actually forget to change the time off parameter to be, you know, longer than the duration of your simulation, that means that you can actually have your particles not collide with surfaces, and that can be a little bit confusing because, you know, you do a simulation, everything's fine, everything's colliding away, and then on frame 200 all of a sudden, pop, you know, it turns off and your particles suddenly fall through the floor. So that's actually a bit of a blessing and a curse. So let's just quickly run through the differences again with this space warp before we actually conclude this chapter. We have time on when the actual space warp becomes active, time off when it becomes inactive. You have reflection here and refraction, and these two work together. You pass on particles to be refracted by reducing the amount of particles that are reflected. So at 90%, only 10% of the particles will be sent on to be refracted, as you can see here. At 50%, obviously 50% of the particles will be reflected, as you can see here, they're being bounced along the surface, and the other 50% are being sent on to be refracted. If I change the refraction to 0, and if I actually change this distortion, you can see that it actually has no effect because none of the particles are actually being refracted. Effectively, that is exactly the same as having the collide option here set to continue. If I have anything other than 0, let's say 25%, you can see that only a quarter of the particles that actually are sent on from here are actually refracted, and the other 75% of the particles sent on are actually allowed to continue onwards. So you've got a lot of control there in actually how many particles get reflected and refracted. Once they're refracted, you can actually pass on the velocity of the collision object using pass velocity, and that is in the refraction part. You can actually change the variation of how much of that velocity is passed on. You can distort the particles away from the normal angle that they would actually normally pass through the surface, which you could say is refraction. That's actually the true refraction value. And then you can actually distort the particles away from the perfect angle that they would actually travel onwards using the diffusion value. So there you go, you can actually diffuse them that way as well. So by using a combination of those two parameters, you can actually get quite a large variance in the actual angle that the particles pass through the surface. And as I said, the other two versions of this particular space warp do exactly the same thing, except with a spherical and a mesh. And I'll quickly show you those, and then we'll just finish off this chapter. I'll just turn off OmniDeflect here, P-OmniFlect, hide it. We'll just go on to the next one, which is S-OmniFlect. Just show that to you here. There we are, there's S-OmniFlect. And these refractions, this is actually quite a good example because these refractions are actually carried out on the particles every time they hit the space warp. So you'll see here the particles come in, they get refracted, and when they go out, they get refracted. So if the particles are going in and out of the space warp, you'll actually see that they get refracted each time. So you can see that there with the spherical space warp, spherical OmniFlect. We'll just hide that again. And here's the U-OmniFlect, and we'll just unhide that as well. There we go. So in this case, we've got the U-OmniFlect. The particles are coming into the tube. They're hitting the bottom of it, and they're being refracted. Obviously, if you didn't want that, you could actually go in here, and you could set a percentage of the particles that get reflected. So we'll say 50%. Now you can see 50% of the particles are actually hitting the tube and actually bouncing along it, and the other 50% are actually passing through the tube. It's quite interesting. We could put that up to 100%, and all of the particles will now just collide with the tube and slide down it. There we go. It's pretty cool. And if we wanted the particles obviously to go down the tube more slowly, we could obviously increase our friction, which we have down here. We've got 6%. Let's change that to 30%. Let's change that to 50%. And now if I play the simulation, we can see I have quite a different result. There you go. So they lose their bounce quite quickly, and then they just slide down the tube because they've only got this 60%. We'll just put it up to 100% and see what happens. There you go. Even then, it's still actually they're being pushed down the tube, and that's probably because of lack of drag. If we put drag on those, they'd actually come to a stop. So that's it. that's it for the collision chapter. That's it for the space warp chapter. As you can see, it's quite a complex topic. We've got the tests on one hand, the collision test, and also the collision spawn test, which we'll come to in an earlier chapter, as it were. The test and the space warp work together. The actual test element is obviously done in the test, and all the parameters for, you know, controlling the kind of bounce and the kind of collision, they're all handled in the space warp itself. So from here, probably the best thing to do is to actually move on to having a look at the collision spawn test and see how that works. That's obviously a kind of hybrid test in that it links together the spawn test and the collision test, and it puts them together, and you actually get this sort of hybrid functionality from the two. Okay, see you in that chapter. Bye.